From correlation to regression. In correlation, we calculated r equals 0.53 as a measure of the association or correlation between two variables. We could plot the variables the other way around, we get the same value of correlation. Correlation is symmetric between y and x. However, for regression, we're interested in predicting one of the variables from the other, and traditionally y from x. So we say the regression of y against x, or y on x. And x is the predictor variable, the predictor variable, and y is the predicted variable. And we're interested in putting a line through these points that's the best fit from the point of view of predicting a y value for some given selected x value. Now, before I turn the regression line on, what line do you eyeball through this as fitting it reasonably well? A fairly steep line up about like that? Okay, I'm going to click to turn on the regression panel here, and down here at red 10, I'll click to display the regression line. Oh, that's not as steep as our eyeballed line, is it? No. That's what always happens unless we have a correlation of 1 between y and x. This line is a little less steep than we might eyeball because it is chosen to meet the criterion of the best prediction of y for a given x. What criterion? That's what we'll discuss in just a moment. But first, let me mention if we put a cross through the means there. So the mean of x is about 3.8, mean of y about 5.2, and there we are, 3.8, 5.2, and the regression line always goes through that point, through the means of x and y. We can mark some values of x and y. Here is x at, say, 4.3, and the corresponding estimate of y, called y hat, is 5.655. Now for the next step, I'm going to use a smaller data set, so things are a bit clearer to see. I'll load the Thomason 1 data set. There it is, and I'll put the regression line through it. The line appears to be perhaps nearly as steep as our eyeballed line because we have a very high correlation. From the point of view of one of these data points, there's some error of estimation. This line doesn't estimate that data point, that y value, accurately. And I can mark those, they're called residuals, as little vertical red lines between the y hat value on the line and the y value for this particular data point. So from the point of view of this data point, the line underestimates y. From the point of view of this data point, the line overestimates y. And these red lines are the errors of estimation, also known as the residuals. Why residual? Well, think of accounting for the whole variability in y. The line accounts for some of it, and beyond that, there are errors of estimation. So these errors are sort of the residual variability of y after we've taken into account the work that the line does. The variability in y has two components, one accounted for by the line and the other by these residuals. Now, least squares linear regression, which is what we're discussing, is based on minimizing the sum of squares of these estimation errors, or minimizing the standard deviation of these estimation errors, minimizing s y dot x, which is the standard deviation of the residuals. Now consider rotating this line around this means point. If we rotated it clockwise, that residual would get larger, this a little shorter, that would get shorter, and so on. If we rotated it counterclockwise, the reverse sort of changes. The criterion for choosing this line and choosing its slope is that the sum of squares of these residuals is minimized. We can illustrate that by displaying the adjustable line. This red line goes through the means point, and I can adjust it. Let me rotate it clockwise. Oh, that's counterclockwise. All right, let's make it very steep. There we go. And the standard deviation of the residuals there is about 1.4. And if I take this way down, it's about 2.8, 1.6, 1.5, 1.4. And it goes down and then starts going up again, 1.4. So let me try and minimize it. Oh, up a bit. I've gone too far, I think. Ah, yes, it turned black at this slope of 0.77, which is very close to the calculated slope using the formula for the regression line. So there is an optimal slope of this regression line that meets the criterion of minimizing the sum of squares of these estimation errors. And from this position, if it's rotated even a little counterclockwise or clockwise, then the sum of squares of these residuals will increase. So this is why this is called the least squares regression line for y on x. I have an alternative display of the same data set, and this is a standardized display. So I've got zy and zx. I've just transformed both y and x into z scores, into z scores. So here are the original data points, and here are the corresponding standardized values for zx and zy. And here I've got a line through the means, which of course goes through 0 and 0, and here I've got the line. Now it turns out that in standard scores, the best eyeballed line has slope of exactly 1, and the slope of the regression line is equal to the correlation, equal to 0.89. Now remember that when we were talking about correlation, I said we can easily change the apparent slope of the eyeballed line by changing these units. And that's quite true. But if we stick with standardized units, so that's equivalent for x and y, and we make this axis the same scale as that axis, then the eyeballed line is always exactly at 45 degrees, a gradient of 1, and the linear regression line has a slope of r. And so when we've got very low correlation, we have a slope that is down round closer to horizontal. And when we've got very high correlation, we get a slope of the regression line up towards 1. There's a small section in the chapter for the reverse regression, regression of x against y, the wrong way round if you like. In that case, the slopes are all greater than 1 here because we're minimizing the residuals in x rather than in y. But if we return to basics here, what is regression telling us? It's telling us that for a particular chosen value of x along here, our best prediction for the y value is read off from this regression line, which has a gradient selected so that the sum of squares of these prediction errors in y is minimized. We're not saying that the x values cause the y values. We're not saying anything about causality. We're simply saying that given this particular data set, the best prediction for a case that comes along, say with a pre-test of 8, will be read off from this regression line at 10.5. And that's a useful tool for understanding this data set, and in particular for predicting values of y, our predicted variable.